The chemical reaction is Reimer Tiemann chemical reaction. This chemical reaction is used to convert phenol into orthohydroxybenzaldehyde. Keep in mind, orthohydroxybenzaldehyde is also known as salicylaldehyde. Okay, the reaction is carried out in the presence of chloroform and strong base. Let me write down the chemical reaction. Okay, in the reaction we convert phenol into salicylaldehyde. We have salicylaldehyde structure, benzene ring, we have OH, and in the ortho position we get aldehyde group. Okay, in ortho position we have aldehyde group. The reagents used in this chemical reaction, we have chloroform, the chemical formula of chloroform CHCl3, and a strong base we can take potassium hydroxide or we can also take sodium hydroxide. Okay, if you look at the product, we can see we are getting aldehyde group at the ortho position with respect to OH. How we get this aldehyde group at the ortho position, we can understand only through mechanism. Okay, always keep in mind, from this mixture of reagents we get dichlorocarbon. Dichlorocarbon or carbene are highly reactive species. They are highly reactive species. Why they are highly reactive? If you look at the structure, you can see carbon is forming single bond with each halogen and it has one electron pair also. Each chemical bond has how many electrons? 2 electrons are there. Here also it has 2 electrons, and you can see this is also 2 electrons. Total number of electrons 2 plus 2 plus 2 is equal to 6 electrons are there. You can see carbon has how many electrons? 6 electrons in dichlorocarbon. Hence you can see its octet is incomplete. It has incomplete octet. This is why it is highly reactive by nature, because it wants to gain 2 more electrons to be in the stable state. It wants to complete its octet. Okay, that's why it is highly reactive by nature. Since it is electron deficient, hence we can also say it is acting as electrophile because it is electron deficient. Acting as electrophile, it is electron deficient. Being electron deficient, it will always attack the place where more electron density is there. And keep in mind, benzene ring, this benzene ring is electron rich. Why it is electron rich? You can see it is having how many pi bond? This is 1 pi bond, this is second pi bond, this is the third pi bond. Okay, total number of pi bonds, how many are there? 3 pi bonds. Okay, and each pi bond has how many electrons? 2 pi electrons. You can see each pi bond has 2 pi electrons. Total number of pi electrons, we got 6 pi electrons are there. Okay, so you can see this benzene ring is highly electron rich. This is the reason once this dichlorocarbon is generated or produced, it attacks the benzene. This is where the chemical reaction starts. Okay, chemical reaction starts. Now moreover, you can see to the benzene ring we have hydroxyl group, and this group is acting as a plus M group. This is your electron donating group. Plus M group is nothing. We have a positive mesomery group. Okay, this positive mesomery group is acting as a electron donating group. That's why it is also known as ring activating group, because they are supplying electron density to the benzene ring. Okay, benzene ring is already electron rich, but furthermore you can see hydroxyl group is supplying electron density. You can see electron density of the benzene ring is increasing. Its reactivity is also increasing towards electrophile. Okay, so you can see attack by the electrophile or the benzene ring will be at the quite faster rate, because you can see it is highly electron rich. Okay, in the mechanism, first of all we understand how this dichlorocarbon is generated, and then we discuss the further course of the reaction. Okay, move on to the mechanism. Pay attention very carefully. This reaction is going to be very interesting. Okay, we have mechanism. Okay, mechanism. You can see in the reagents we have chloroform and strong base. The structure of chloroform we have CH, and to the same carbon you can see 3 halogens are attached. In general, these halogens are acting as a minus I group, negative inductive group, and we have learned in general organic chemistry, as the minus I group increases, acidic character of the substance also increases. Okay, why? Because they are pulling electron density, and hydrogen as a result is also losing electron density. And when it is losing electron density, hydrogen is supposed to carry partial positive charge, and this hydrogen will be liberated from here in the form of H+, because it is losing electron density to, you can see, haloelectronegative elements. Okay, So hence we can say due to high minus high group, you can see this hydrogen is what? Acidic hydrogen. Okay, acidic hydrogen. Keep in mind chloroform is acidic by nature due to the presence of minus high group. Okay, so this is what acidic hydrogen is there, and in this region we have strong base is also there. Strong base we have potassium hydroxide. Being a strong base will liberate OH minus ion very easily, and this OH minus ion will attack the acidic hydrogen. Okay, so that they can neutralize and settle. So you can see OH minus ion, the flow of electron density is coming this side. As a result, this electron density will move towards a more electronegative element. Okay, to avoid the repulsion. Okay, when this electron density is coming this side, you can see Cl being more electronegative will also pull the electron density. Why? Because you can see halogens in general are better leaving group because they have the larger size. Okay, now pay attention very carefully. When this 1 mole of potassium hydroxide, a strong base, approaches chloroform, you can see in this entire reaction 1 mole of HCl is liberated. You can see 1 hydrogen and 1 Cl is liberated. Means 1 mole of strong base neutralizes 1 mole of strong acid. HCl is what? Strong acid. So you can see what happened exactly. KOH is neutralizing strong acid and converting into KCl, and H2 is there. This is what happens, and remaining whatever is left, that is dichlorocarbon. This is what we are looking for. You can see this is what dichlorocarbon is there. So let me write it. This is what we have. Dichlorocarbon is there. Highly reactive species. Its octet is not complete because it has 6 electrons. That's why it is reactive. Highly reactive by nature. Okay. Now we come to phenol. Okay. Now we move on to phenol. Pay attention very carefully. We have phenol, and phenol is what? Aromatic alcohol. Phenol is aromatic alcohol. We have OH is there. Okay, listen very carefully. In general, aromatic alcohols are acidic in nature, more acidic in nature than aliphatic alcohol, because in case of aromatic alcohol, resonance is there. When the resonance is there, so whatever the anion is generated after losing H plus ion, that anion due to the resonance gets stabilized. Now pay attention carefully. Now let's say if I break this bond, it is having partial positive charge, it is having partial negative charge. Oxygen being more electronegative will carry partial negative charge, and this negative charge is a part of resonance. You can see this double bond. We can mention this is what we have. This double bond is there. This double bond here we have double bond. Sorry, double bond we have. Double bond is there, and single bond negative charge. Double bond, single bond negative charge. Keep in mind, double bond, single bond negative charge, double bond, single bond positive charge, double bond, single bond lone pair. These are the examples of conjugated system. And if there is a conjugated system, there will be resonance. You can see double bond, single bond negative charge is there. So resonance is there, and when resonance is there, this negative charge participates in the resonance, hence it gets stabilized. That's why this phenol is acidic in nature. We can say this hydrogen is acidic in nature. Acidic hydrogen. This hydrogen is acidic hydrogen, and better acid is the acid. You might have learned better acid is the acid which after losing H plus ion, its anion gets stabilized. Okay, its anions gets stabilized. Okay, so now let's continue the reaction. Just I explain the acidic character of phenol by resonance. So we have phenol is there. In the phenol, the hydrogen attached to oxygen. Hydrogen attached to oxygen is this is what? Acidic hydrogen, and we have a strong base. Strong base, being a strong base, will immediately liberate OH minus ion, and it will attack acidic hydrogen. Okay, and keep in mind, strong base, the presence of strong base will be there in the chemical reaction till the end of the chemical reaction. Its influence will be there. Okay, now when it is attacking acidic hydrogen, as a result, oxygen being more electronegative will pull the electron density. Okay, so you can see H2 is liberated. From here, H2 is liberated. Here we have K plus is also there. K plus can be attached to O minus. Okay, O minus. And from here we are getting O minus. O minus there. This is what we have, O minus. And this negative charge over the oxygen is in the stable state. This is what we have, phenoxide ion is there. We have phenoxide ion, and this is highly stable due to the resonance. Okay, double single negative charge. Now this negative charge will participate in the resonance. When this electron density is coming this side, okay, so you can see this electron density will move in opposite sides to avoid the repulsion. Okay, to avoid the repulsion. Okay, so what will happen? You can see When this electron density, this ring is there, cyclic ring is there, this bond is safe, this bond is also safe, and now you can see over this, we have oxygen single bond already there, and when this electron density coming this side will generate double bond. Okay, this electron density moving towards ortho position, here we have the negative charge. Now you can see ortho position is what? Electron rich, because over this electron pair is there. One negative charge is equal to 2 electrons. And dichlorocarbon will come into the picture now, because it is looking for 2 electrons. Immediately it will get attracted to towards ortho position, because here we have accumulated electron density. Okay, pay attention very carefully. This is going to be very interesting. You can see now we have dichlorocarbon is there, which is electron deficient species. You can see dichlorocarbon, it will supply electron density. Okay, when it supplies electron density, it will attach to the ortho position, because new bond formation is there. Okay, this cyclic ring is there, this bond is safe, this bond is also safe, double bond O is there, and here we have C and it is Cl2 is there. Keep in mind, carbon in dichlorocarbon is accepting electron pair, that's why it will carry negative charge. Here we have the negative charge. Okay, now this is the intermediate substance formed in the reaction. Keep in mind, Reimer Tiemann chemical reaction, intermediate, this is what we have, intermediate substance, and it is highly unstable. Why? Because pay attention carefully. This is not benzene ring, this is the cyclic ring, because it does not have aromatic character. Why? Because you can see in this is what we have, benzene ring. This is benzene ring is there, because it has how many pi electrons? It has 6 pi electrons are there. By Huckel's rule, it has 6 pi electrons, hence it is having aromatic character. One of the factor is there. Okay, so you can see it is having how many pi electrons? 2 pi electrons plus 2 pi electron, total how many? 4 pi electrons are there. It has lost its aromatic character, hence it lost its stability also. To be in the stable state, again it will have greater tendency to be in the stable state by attaining its aromatic character. So it will arrange itself in such a way so that it can get its aromatic character. So now if you pay attention here, you can see in this carbon, you can see we have one hydrogen is present, and if this electron density is coming this side, so you can see one bond will be generated, and if one double bond is generated, you can see its aromatic character will be attained and its stability will further increase. Okay, so automatically it is happening, spontaneous process, we can say. This electron density is coming this side, as a result you can see this carbon is already forming 4 bond, and if it is going to form new bond, it has to break its old bond, because its valency is already satisfied. Okay, so as a result, oxygen being more electronegative will pull the electron density. Okay, when this electron density is coming this side, means hydrogen is losing electron density, hence it will be liberated in the form of H+, and this H+ will be inverted by C-, because positive negative attraction will be there. Okay, now what happens, you can see cyclic ring is there. Here we have the cyclic ring, this bond is safe, this bond is also safe. Here we have single bond, because one bond is broken, oxygen is pulling electron density, and this new bond is generated. Now this hydrogen will attach to carbon. Here we have C and we have CH, and you can see 2 halogens are there, 2 halogens. You can see aromatic character is attained. It has 6 pi electrons. We have dihalide. What kind of dihalide? Gem dihalide, because 2 halogens are attached to the same carbon, gem dihalide. And you can see, as I said, presence of strong base will always be there, since water molecule is also liberated during the reaction. So we have aqueous potassium hydroxide. Okay, you can see alkyl halide reacting with potassium hydroxide in aqueous medium. It is an example of what? Nucleophilic substitution reaction. Okay, Cl will be substituted by OH group. Okay, how many Cl are there? 2 Cl are there, so we can take 2 moles of potassium hydroxide. 2 KCl will be gone, and in place of Cl, OH will attach. Okay, in place of Cl, OH will attach. Okay, OH will attach. In general, what happens, you can see, if we have alkyl halide is there, it is reacting with potassium hydroxide in aqueous medium, so KCl will be eliminated from here and we get alcohol. This is what is going to happen. So now you can see nucleophilic substitution reaction taking place. Here we have the benzene ring. Okay, benzene ring, we have O- is there, we have CH, it is OH is there, this is what we have OH. Okay, from here 2 moles of KCl eliminated. Okay, now again you can see this is in unstable state, because these are the bulky group. These are the bulky group attached to the same carbon, so repulsion will be there. Okay, cloudiness is there. So you can see repulsion. To avoid the repulsion, we remove water molecule so that it can be in the stable state. And once we remove water molecule, so you can see we are left with only one oxygen. This oxygen is attached to CH. This is what we are looking for, because this is, we have aldehyde group CHO. This is, we have O minus is there. Okay, we got aldehyde group in ortho position. From this H2O we get H plus ion. This H plus ion will be attracted by O minus ion. As a result, we get a final product, that is salicylaldehyde, OH. This is what CHO is there. CHO, we have salicylaldehyde. Aldehyde is there. Salicylaldehyde. We got salicylaldehyde. It is also known as ortho-hydroxybenzaldehyde. This is what benzaldehyde. In ortho position, we have OH group with respect to CHO. So this is how we convert phenol into salicylaldehyde, ortho-hydroxybenzaldehyde.